So I'm going to go through really quick what we did on the board on Wednesday with deriving that formula, because we didn't have it in the video. And then we're going to do a few more projectile motion problems. We did the baseball problem on the board last time, trying to figure out if the guy would have a home run or not, if it would go over that 10-foot fence. So we're going to back up and just do some basic problems where we're not trying to decide if it's a home run, just what is max height, what is range, things like that. But then we'll look at a couple more challenging ones. So these are similar to what we were doing with just knowing acceleration, knowing some initial conditions. But to derive that projectile motion formula, we've got to start with unknowns. The one thing that we do know is, acceleration is straight down at 32 feet per second, if we're in feet per second, or really quickly, yeah, because I did it on the board instead of in the video. If we're in meters per second, it's negative 9.8. So it just depends on what units the problem is using. I'm just going to work it out in feet per second. If we did it in meters per second, it would just end up changing one coefficient in the problem, and that's it. So this is the only value we truly know, is the gravity. We would also be told possibly some initial velocity. And what angle that velocity is at, and some initial position. And it's usually just at a height. Usually just has a height to it. These two are a magnitude and an angle. So to get them written as a vector, we're going to have to take a magnitude and an angle and split them into components. And the way that we said we were going to do that is our conversion formula that said the x component was magnitude cosine theta, the y component is magnitude sine theta. So we said v sub 0 cosine theta I plus v sub 0 sine theta j. So that takes our initial velocity as a magnitude and a direction and writes it as a vector. And then our height is, initial position is just a height, so it is going to just have a j component on it. So we can use what we know about acceleration due to gravity, and we can use integration to work our way backwards to a position function. So if we integrate our acceleration with respect to t, right now the I component is 0, and the antiderivative will be a constant. The j component is a constant, so its antiderivative will be linear plus our arbitrary constant. This is our starting point for our velocity function. And we are told that if you plug in 0, you should get this. So we'll plug in 0 to what we got for the antiderivative and compare it, and that's going to allow us to solve for the C1 and the C2. So if we plug 0 into ours for the t's, that just leaves C1i plus C2j. And when we compare it to this, we get that C1 is v sub 0 cosine theta, and C2 is v sub 0 sine theta. So we integrate our acceleration function. That introduces some arbitrary constants. We plug 0 into that antiderivative for t and compare it to the initial condition we were given for velocity. And we're able to solve for those arbitrary constants. So now we've got a velocity function. V of t equals, we were able to solve for c1. That's v sub 0 cosine theta. That's our I component. And then this is our j component. It's negative 32t plus c sub 2, which what we found was v sub 0 sine theta. That's our j component. And then we need to go through the whole process one more time with an antiderivative to get back to a position function. So remember, the variable here is t. The v sub 0, that's the magnitude of our initial velocity. That's going to be a number. The theta is the angle of the initial velocity. That's going to be a number. So when we're integrating, we're just integrating the t's. Everything else, there's going to be numbers in those spots. So if we integrate one more time, we'll get a starting point for our position function. So all of this is just going to be a number, v sub 0 cosine theta. That's just going to have a value. So it's antiderivative, we're just going to throw a t onto it. Plus an arbitrary constant. And then for the j component, I do have a linear term. So if I do my power rule, I get negative 16t squared. I have a constant term, so I'm going to throw a t onto that. And an arbitrary constant. And we were given an initial condition for position. We were given an initial height. We are told that r of 0 is hj. We'll be given an initial height that the projectile will start at. So if we plug 0 into what we got for our antiderivative, if we plug 0 in for the t's, we can compare it to this and solve for our new set of arbitrary constants. And then we'll have just the basic setup for projectile motion that we can use for all of these projectile motion problems. Oops. So I'm going to plug 0 in for our antiderivative. We're going to plug 0 in for t. We just get c1i plus c2j again. And according to our initial condition, this should equal hj, which means c1 equals 0, c2 equals h. So our projectile motion position equation is v sub 0 cosine theta t I and negative 16t squared plus v sub 0 sine theta t plus hj. Now the only thing that's going to change if we're not in feet per second is that negative 16. All of the other pieces, the v sub 0 cosine theta, v sub 0 sine theta, that came from velocity, and the h came from position. This piece came from acceleration. It started off as a negative 32, but in the process of doing two antiderivatives, we ended up cutting it in half because of power rule. So if for some reason we had a problem where we were doing meters per second, we would cut our negative 9.8 in half. And what would the coefficient be? Negative 4.9, right? So for feet per second, we use negative 16 in that spot. But if it was meters per second, it would be negative 4.9 t squared in that spot. Everything else would be exactly the same. So having this written out as a vector valued function takes into account what's happening horizontally. That's our x component. What's happening vertically, that's our y component. And the time at which all of that stuff is happening, that's the parameter t. Some of the questions we're going to be asked only deal with one piece, one component. So we could break this up into parametric equations and say, well, what's happening horizontally is just our x component, v sub 0 cosine theta t, and just work with it individually. And that might be easier to do. And what's happening vertically only deals with the y component, which is negative 16 t squared plus v sub 0 sine theta t plus h. And it might be easier to just work with that individually rather than working it with them together written in a vector valued function. So just like we did when we wrote equations for lines in space, we could take each of the components, we could take each of the parametric equations and write them components as a vector valued function, or we could keep them individually as a set of parametric equations. So it's the same idea here, except they're just not linear. The y component's quadratic. So what kind of questions did they say they could ask us about where we would want to use the horizontal equation? The range, right. If they asked us anything about the range, we would be using the x equation. The range of the projectile has to do with how far horizontally it has traveled. And what could they ask us where we would have to use the y equation? Height. Anything about the height of the projectile, usually maximum height, is a very common question that they would ask us about. So I'm going to put it in parentheses, max, usually, but really anything having to do with the height of the projectile. So we did that one baseball problem last time where we had to use both of these equations to figure out if we were going to, if the guy was going to get a home run. We're going to take a step back and just do a couple more basic problems. But we're going to do quite a few just to get a handle on these equations. If you have your handouts, we are just going to do them straight from the handout. That way I'm not having to rewrite the entire problem every single time. And the first one we're going to do is number 30. It says determine the maximum height and the range of a projectile fired at a height of 3 feet above the ground with an initial velocity of 900 feet per second at an angle of 45 degrees above the horizontal. So they give us all the information that we expect. They give us initial height or initial position, initial velocity, and an angle. V sub 0, theta, and h. They want us to figure out maximum height and range. Maximum height and range. So let's write out what these pieces are going to look like. I'm going to write out the entire vector valued function first. And I'm not going to round any of my decimals yet because that might throw my final answer off. Our angle is 45 degrees. Sine and cosine of 40 degrees is not an exact value. It's got a radical in it. So I'm going to leave it with a radical. It's not a rational number. So I'm going to write out a position function, a vector valued function for my position. But really when I go to solve this problem, I'm going to separate them, but I just want to know what it looks like for now. So R of t equals, the horizontal just has to do with initial velocity and angle. So what's the magnitude of our initial velocity? 900. 900, and it's in feet per second, so that's important also. And with the x, we do cosine, and the angle is 45. And that is times t, and that's our I component. And because we're in feet per second, what's the coefficient on our t squared? It's either negative 16 or negative 4.9. It's negative 16. And feet per second is going to be negative 16. So negative 16 t squared plus, and then 900 sine 45. And what height do we start at? 3. Sine and cosine of 45 both have the exact same value. And I'm not going to write a decimal yet. We will eventually, but I'm going to keep them exact right now. Sine and cosine of 45 degrees are both radical 2 over 2. So that's going to make this 450 radical 2 ti plus negative 16 t squared plus 450 radical 2 t plus 3j. That is the vector valued function that represents the projectile motion for whatever this thing is that we're launching. And it takes into account what's happening horizontally and what is happening vertically. What do you want to do first, max height or range? Range, okay. Let's start with range. What did we say range was last time? That's the x equation. Ethan, you said distance is the horizontal distance it travels before it hits the ground. Right. We want to know the total horizontal distance it travels before it hits the ground. And that last part's really important because we need to know, technically we can plug any value in for t in that first equation and it'll just go forever. We need to know when it hits the ground so we know what value to plug into the x formula. I can plug 50 seconds in for t. And it's going to give me a big value for my x. I can plug 1,000 seconds in for t. It's going to give me an even bigger value for my x. We have to know when it hits the ground to know when to stop its forward motion. So the first step is to figure out when it will hit the ground. And that is a height of 0. So first step is, when is height going to equal 0? Well, the height is the y equation. So negative 16t squared plus 450 radical 2t plus 3 equals 0. It's not going to factor, but you could use quadratic formula or you can graph it on your calculator.
Go do that in your head. Come on, you're a math.
It's going to be negative 450 radical 2 plus or minus the square root of 450 radical 2 squared minus 4 times negative 16 times 3 over negative 32.
39. Yeah.
So 39.78.
I didn't round.
39.78. We're going to have to round at some point. Huh? It's in seconds. It is a long time, yes. But it had a really large initial velocity. 900 feet per second is pretty big.
When you factor in air resistance.
No air resistance. We don't like air resistance in this class.
I don't like it in any class, honestly.
So we're going to say 39.78? All right. So you can get that with a quadratic formula. You can also get it if you type this into y equals. You're going to have to adjust your window and find the x-intercept. You're not going to get it in your standard window. You're going to have to play around with your window in order to see the x-intercept. There's 2 of them, but one of them's negative. So we're not going to worry about that one. So this thing takes off, 39.78 seconds later, it lands. We want to know the horizontal distance it has covered in that time. So we can take this 39.78 and plug it into the x equation. And the x equation says just do 450 radical 2 times your t value. Here's our x equation. There's the x portion of it. This is the y portion. The x portion is almost always going to be really easy. It's just going to be linear. So we just have to multiply that time by 450 radical 2. $25,000. Anybody else get that?
Yep.
That's a big number. So tell me again, 25,000. 350. So I'm going to say 316. It's about 25,316 feet. That's almost 5 miles, right? 4.8 miles. That's a long ways. How far do bullets don't even travel that far usually, do they? Bullets just go a mile or 2. They can go farther? Okay.
What's the longest
It was like a mile and a half. Yeah. And some bullets are lethal up to a mile and a half, yeah.
Okay.
And that's fired up flat trajectory. I know 22 with the right conditions can fly like 5 miles. That's what they say.
Mm-hmm.
But I mean, that's fired at I think 1,300 feet per second.
So this is like equivalent to a bullet.
Yeah. That's like a air rifle maybe.
Mm-hmm. But this thing's at an angle. You usually wouldn't fire a bullet at a 45-degree angle.
Okay.
You wouldn't fire at a 45-degree angle hoping to hit a target 5 miles away.
It's like my friend. It's like my friend. First time I shot my AR. He was trying to do rapid fire, so he shot it once and he tried to pull it again, but his rifle was up here. My rifle was up there. So he shot it at an angle, and I saw it hit like the field, like a mile away, and I was like, gosh. I didn't let him shoot.
All right, for max height, we want to do this with calculus.
Huh?
We want to do maximum height with calculus.
Yeah.
Yes. We could type it into y equals and find the max that way, yes. But just to refresh our brains with some calculus 1 concepts, we can find maximum height with calculus by doing derivative equals 0, yes. We have a max when velocity changes from positive to negative, okay? In order to go from positives to negatives, you have to go through 0 in between. Okay, velocity is the derivative of position. And all we care about is height here, because we want max height. So if our y equation, just the y of t, is negative 16t squared plus 450 radical 2t plus 3, y prime, negative 32t plus 450 radical 2. We want to know when that's going to be 0, because that's going to be the vertex of our parabola. That's going to be the turning point on our parabola, where it changes from increasing to decreasing. Is that the answer they want?
No, I want the actual height.
Right, that is not your answer.
You have to use your calculator.
Right. Not the graphing part, though. The maximum height occurs at 19.89 seconds. So now we have to take that time and plug it into the height formula to figure out what the actual maximum height is. So we're going to find the y value at 19.89.
$331.125. Pretty high. You can shoot over a mountain in front.
It's more than a mile.
Shoot over the biggest mountain in the eastern half of this.
All right, Mr. Brand Games champ.
Just saying. No, I'm not champ yet. I still got another week. I don't know. Probably won't beat this next team. So.
Look at Mr. You have 7 wrongs.
So for max height, we didn't ever have to leave the y equation. It's all in the y equation. But for the range, we did have to use both of them. First, we have to know when it hits the ground, and that's a height of 0. And then we had to use that time to go back to our x equation. Do you think we could make this projectile go higher or farther by changing the angle?
No, I suppose it's gonna go. Make it go higher. Maybe if you increase the initial velocity.
Definitely if we increase the initial velocity.
But keeping everything else the same. A little bit more power behind it.
I would like us to try something real quick. Does anybody have any questions first? So we can get practice with one more problem like this.
Right, shoot.
Okay.
I just didn't do it by trial. You said October.
What?
No, I was just reading what she said.
Worst to best. No, it's mine.
Of course, you put the old guy at the bottom. It's worst to best, Cody. That's what Ethan said.
Meaning that I'm the worst.
I want 69 degrees. Just because you want to let me with the shirt. Just 'cause.
Can I have 45 degrees?
We just did it! No!
46.
200 degrees.
What? You shoot yourself?
No.
85, that's slow. Make it be 90 degrees. Cosine 69.
Everything else is the same, right?
Everything else is the same. You're just going to change your angle. Yep. You can pretty much, if you wrote down what we did for the last problems, pretty much go back in and change the angle. Everything else can be exactly the same. So everybody's got a different angle. We want to go back in and see what the range and the max height is going to be for your angle. And then we're going to come back and look at the values and see how these different angles change the range and the max height.
He wants to round.
Doesn't matter. Nearest whole number would be fine. For times, probably keep it a tenth. But for the heights and the range, you can probably go to the nearest whole number, because they're probably going to be really big numbers. Your what? Your angle is 10. Keep it at 10. Oh, cosine of 10. Keep 4 decimals for that one.
I can't.
Whatever you want to do.
My height.
Or just in your calculator, type cosine 10 when you do the calculation.
My height is 11,033 feet.
Are you positive?
Oh, 34 feet.
Max height?
Yes, 11,034 feet. That's for your whole number. Yeah. Distance is not very far.
Let me know if you need some help. Or ask your friends, your neighbors.
Okay, and it goes 16,939 feet.
So 69 degrees, you get less range but more height.
Yes.
Yeah, I paused it just so we could get the table filled in. So it was a bunch of work, yes. But there's a pattern. Look at the pattern to the numbers. So I put these in order. I put our original one that we just all did together in red, where it goes in the middle. What pattern do we see?
Range is like a parabola.
Range is the parabola, right? The numbers start to get bigger. 45 is the biggest, and then they get back smaller. And then what do we see going on with max height? It just gets bigger and bigger and bigger and bigger. Yep. As the angle goes up, the max height goes up.
So it's not equal to max height.
Yes. So if you did, if you shot it straight up at 90 degrees, that's when you would get maximum height. If you shoot it at 45 degrees, that's when you get maximum range. And yeah, and then we can start changing the velocities and see all of what that stuff does. But if we do it at a higher angle, it'll go higher, but it will land sooner. Less range, more height. So let's say that was 60 degrees. Less range, more height. If we do a smaller angle, it was less range and less height. So there is a way to get more height. There's not a way to get more range. 45 is the max for range. Anything different than 45 and you're going to get less range. There is a way to get more height, and that is to go all the way up to 90. Anything bigger than 45 will get you more height. Okay? So for maximum range, you want 45 degrees. For maximum height, you want to go as close to vertical as possible. So, because that will take all of your velocity and it will direct it straight up. Okay? But if you have to split your velocity into a vertical component and a horizontal component, then that splits it.
Shouldn't 10's range be shorter than 60?
Say it again?
Shouldn't 10's range be shorter than 60?
Yeah, probably. I don't know. Let me see. Yeah, definitely way shorter. You got a baby curve, Ethan. Should probably be even shorter than that too.
So So much.
60 might even be.
Outside of the.
Well, I didn't make 60 long enough either. 60 should be about 2/3 of 45. Bottom line, 45 for maximum range, 90 for maximum height. Okay, they all end up with that little curve shape though, except for the 90, which is just gonna go straight up, straight down.
I don't count the wind that you have. Wind.
No wind resistance.
Not wind
I
resistance. You
know.
have wind pushing it or pulling it.
That's considered wind
So we're
resistance.
shooting bullets in a vacuum.
Everything's in a vacuum. We like vacuums here. Yes. We don't want to account for anything else except for the math.
Now, there's terrorists on the internet there. Like, well,
No terrorists.
There's no oxygen. Without oxygen, you can't probably.
yeah, you can't fire a gun in the vacuum too. I think you can.
I mean, if it's like, if you have a little air tank, how are you gonna get the spark?
Spark is gonna be inside the.
Yeah, the spark's inside the bullet.
Yeah, because it hits the primer. Primer is not
There's
black
no
powder.
oxygen in there. That's what.
The bullets are already sealed.
What's that?
Yeah, but like you
But
should,
when
you
they
should have
when
gone.
they
You should have gone
produced the
underwater.
bullet, they had some oxygen in that part. You're Google it. Can you fire a bullet from space?
Anybody ever fire a bullet in space?
I don't think they're allowed to take bullets into space.
I don't think so. Either.
It's dangerous. They can't even take some bullets.
Yeah, you're.
Or like the, not carbon, or like this block.
We're gonna do one more real quick.
Get a space time. For what, break or something?
Spring.
You have to leave early today too, right? Did you say that?
No?
I'm pretty sure you did. Okay, you're early. It's 2:30.
We're gonna look at number 38.
Take back the body.